Today I'm going to use Ray Optics, a Python package for geometrical ray tracing, to evaluate an aspheric singlet from the ThorLabs parts catalog by ray tracing. I'll also show how to perturb the lens element's position and evaluate the effects on the image. I'm using the Jupyter Lab and I've already set up a Jupyter notebook. I've initialized my environment by importing the Ray Optics environment file. This provides Python definitions that are useful in running Ray Optics. I've downloaded the part in question from the ThorLabs website. You can search on the part number and you get the information about the part and a selection of formats that you can download the information with. I picked the Zemax format and copied it into my test directory. At this point, I'm going to import the file, which was done successfully. I added the info keyword to get some additional information about the import process itself. A tuple with 2 dictionaries is returned. The second one is what I'm really interested in. This tells me that there were glasses in the model file that are not in the glass catalog set that Ray Optics uses from the optical glass package. The Zemax import process wrote a file into the directory containing the Zemax file based on the same file name plus a template with an SMX extender. And if we look at this file, we'll see that there are 2 materials defined there. One is a substitute material. We found that one of the glasses was named BK7, and that's not an exact match with the current shot catalog. But there is a similar glass, NBK7, and what we did in the import process was substitute that glass for the BK7 glass. But there's another glass here that isn't in any of our catalogs, and it is apparently from the LightPath catalog. So we'll go to the Google and search for LightPath and DZK3M. And right at the top of the list here is a data sheet for the glass. So we'll click on this. And we see that the optical properties for this glass are listed here. Gives us a variety of information. One thing of importance for us to understand is what wavelength the material is going to be used at. The usual convenient way of specifying an optical glass with an index and V number is really only adequate in the visible wavelengths. In this case, we have a lens file that's going to be used in the infrared at 1550 nanometers. So we want to use refractive index information that's in the infrared. And we can copy paste this information into a text file and use that data to create a glass definition called an interpolated glass type. And we'll show the file that I cheated and prepared earlier, where we have BK7, the substitute glass, and our new glass, an interpolated glass type with the material name, the catalog being LightPath, and pairs of wavelength refractive index information. Now we changed this file name to be the same file name as the Zemax file with a SMX extension. And so if I repair the file name from my original subterfuge and then go back and restore the file again, and we look at info, we'll see that now we have the substitute glass and the interpolated glass definition being used in the model, and we no longer have glass not found or glass substituted in the info output. So now we want to set up some convenient aliases that are very commonly used in ray optics functions. one for the sequential model, one for the optical specification, and one for the paraxial model. And if we look at the wavelengths for our spectral region, we see, yes, it's in the infrared. It's at 1550 nanometers. And we can list the model. And we see two elements. A plano-convex aspheric element and what appears to be a plano-parallel plate. We can also calculate the first order data, and we can go back to the original catalog specification and see that the focal length that we have in our model and the focal length on the data sheet are matching at 1.49. So it looks like we've brought the element model in correctly. So now let's generate a lens picture. We can use the interactive layout figure class that integrates into the Matplotlib Python plotting package. We tell it what the optical model is, to draw rays and to turn off the paraxial layout, and this is what we have. We have a very steep aspheric surface and a plain old window in the back. We can also look at transverse ray aberrations. Auto-fitting the data gives a very fine scale in this case. This is very well corrected at the central wavelength for the optical element. Now, it might be more likely that you'd use a range of wavelengths. And so you can change the spectral region to sample more than just a single wavelength. Here, I've upped the range to the coding used on the part. So from about 1.05 nanometers or microns to 1.7 microns. We update the model after we make the change so that the ray optics database knows that this significant parameter has changed. We refresh the aberration plot. You can now see that the scale has been changed to fit all the data in the plot. It's about central wavelength is what we had before, and the extreme wavelengths, we see that we have extreme wavelengths, so we have uncorrected axial color, and this is no surprise. We can list the model, and we can use an alternate model listing command, listsg, for list surface and gap, which is useful because it will allow us to look at element decenters or surface decenters in our model, and that's what we want to do. So one thing we can do is, what we want to do is we want to be able to decenter or laterally shift the first element from the optical axis. So we want to be able to take this element and shift it up or down as a demonstration. So there are a couple of things. One is that we want the ray bundle to stay directed along the axis. So we want to separate the definition of the stop surface here on the first surface. We actually want to put this on a dummy plane in front of the lens element. So we will laterally shift the lens element, but the stop plane, which is what the rays get aimed at, will stay the same. So we take a quick look here at what the actual surface definition is. We see that the first surface has an even polynomial, a sphere with a conic constant and aspheric coefficients up to 12th order, and it's a transmitting surface. So what we're going to do is we're going to add a decentered surfaces to both the first and second surface. And if we list out the model, after we do this, we see that now we have decentered surface parameters on the first and second surfaces. And a decenter is defined by a translation and by a tilt. And the tilt is alpha, beta, gamma Euler angles. The Euler angles would be converted into a rotation matrix. So this information gives you a translation and a rotation matrix. We define these surfaces as a local decenter type and what we call a reverse decenter. A local decenter applies a translation first and then a rotation, whereas the reverse decenter applies the reverse, the inverse of the rotation, and then subtracting the translation. If we want to laterally offset the lens element in the y direction, say by 0.2 millimeters, we set the second element of the translation vector of each of the surfaces to 0.2. Now if we list the model again, we see that the surfaces are decentered and that the y component value is 0.2. And because the second surface is a reverse decenter, we'll see that the optical axis comes back to the original position. Now what we want to do is take care of the stop definition. I'm going to add a dummy plane here and list our model. And we see that here we have the dummy plane on the first surface and the stop, and we now want to look at what the current surface is and set the stop to the current surface. Now when we list the model, we'll see the stop is now on the front dummy plane. Now we update the model and we redo the layout, and we see that yes, the element has moved up by 0.2 millimeters. We see that the ray bundle is aimed the same as it was before, with the central ray coming in along the optical axis and now being deviated by the offset element to generate an off-axis image. And we can look at the aberrations that were produced again by doing a refresh of the aberration plot. And we see the rays at the very edge of the aperture are being affected by coming in at a more eccentric angle and creating flare. But basically the remainder of the beam that crosses the central part of the element is unchanged from an aberration standpoint. So that's a demonstration of how to import a lens element from a commercial catalog, and how to set it up to do some perturbations on lens positioning and to see what the impact is on the ray trace results. I hope you found this helpful.